Now that we've learned shortcuts for proving triangles congruent, we're going to talk about how can we use congruent triangles. And the main thing we use is called Cpctc. And you'll get used to saying that really quickly, but that stands for corresponding parts of congruent triangles are congruent. So what does that mean? Well, if we know that two triangles are congruent, then it means that all of their corresponding parts are congruent. And that kind of makes sense by, the definition of congruent triangles, right? So we've learned all these shortcuts that only require three corresponding parts to be congruent. So we still have three other parts that we haven't shown congruent, and this theorem, Cpctc, allows us to say that and justify why we can say all the other corresponding parts are congruent. So let's do some proofs. So here we're given I is the midpoint of CM. So think about how you're going to mark that in your diagram. I is the midpoint of CM. That means that CI and IM are congruent. I is also the midpoint of BL. So IL and IB are also congruent. We see that we have 1 and 2 are vertical angles, so those would be congruent. So it looks like we're going to be using SAS to show that these triangles are congruent. But notice what we're trying to prove. We're trying to prove that CL, this segment, is congruent to MB. Notice that we don't have a direct way of getting there. So what we're going to do is prove that the triangles are congruent first, and then we can say, well, those segments are part of those triangles, so we can then know that they're congruent. Okay, so we're doing flow proofs in this lesson, just to give you a different experience. So we have the two midpoints that are given. So I'm going to put given on both of those. From this statement, we know that CI and IM are congruent. Remember, we mark those, and that was the definition of midpoint. And we also said IL and IB, and that's also the definition of midpoint. Then we said that angle 1 and angle 2 are congruent because they were vertical angles. So because of all of these, remember this is our SAS, so here's our A, here's our S, here's our S. So SAS, remember they don't have to be in order of SAS in your proof. So I don't want you to think we're trying to do an illegal move here by doing SSA. That's not what we're doing. We are doing SAS, and we have to look at the diagram to verify that that's actually what we have. So because of that, we have triangles congruent. So make sure you're doing an appropriate congruent statement. I'm going to go from C to I to L, C, I, L. So that means I have to go in the other one, M, I, B. And those are congruent by SAS. And so now, because I have congruent triangles, I can state my proof statement, CL is congruent to C to MB. CL is congruent to MB. And the reason is the new thing we just said, Cpctc. All right, so here's another proof. So we are given that SA is parallel to NE. So SA is down here. That's parallel to NE. And then SE and NA are parallel. So notice I'm marking them with my arrows. And we're trying to prove that SA is congruent to NE. Now, a very common thing people like to say is, well, these are parallel, so therefore they're congruent. That is not an acceptable reason to show sides are congruent. Okay, we do not know that. What we do know from parallel lines are angles. So look for your angles. Look for alternate interior angles, corresponding angles, alternate exterior, and corresponding consecutive interior. So if I trace this parallel line and this parallel line and use that diagonal as a transversal, you see it makes that Z shape with angle 3 and angle 4. So those will be congruent because of AIA. And then we also have these lines parallel, so trace those. And again, we're going to use that diagonal line as our transversal. And that's tracing out angle 1 and angle 2. So those will also be congruent by AIA. And then we have that shared transversal in the middle, that side in the middle, so that'll be congruent to itself by reflexive property. So let's write that up. We've got angle side angle happening with these triangles. So that's what we're going for. And then remember, we're going to go one step further and say then SA is congruent to NE after we've shown the triangles are first congruent. Okay, so you got to show triangles congruent first, and then you can say those segments that don't really have a relationship other than they're part of the triangles. Okay, so this was given. SA is parallel to NE, and so is this. And we said that 3 and 4 were congruent by alternate interior angles. And then we also said that angle 1 and angle 2 were congruent for the same reason. And remember, if you like the 2-column proof, you could say these in 2 steps. You didn't have to split it up into 4. That's just how they did it with their flow proof. And then we also said SN is congruent to itself. That's the reflexive property of congruence. Again, the reason they split them up is in a flow proof, they want to show that these 3 things prove the triangle congruent. So that's your ASA. And make sure you write an appropriate congruent statement for your triangles. I'm going to go NES. So NES is congruent to SAN. Okay, and again, you don't have to do it in the same order I did. Just make sure to change the order of the second triangle to match your first order. So we showed that those triangles are congruent, and remember what we're trying to prove. We're trying to prove that SA is congruent to NE. And what is that new theorem? Cpctc. We know that's true because they're parts of those congruent triangles. All right, so we're going to be doing more proofs in class, and please feel free to ask questions if you don't understand that new theorem.